Hey everybody, welcome back. I'm going to continue on tonight with Chapter 9, looking at redox reactions. Leo the lion says grr, right? We've got oxidation type reactions. Losing electrons is oxidation. And we've got reduction reactions. Gaining electrons for an atom or ion means reduction. Leo, losing electrons, oxidation. Gaining electrons, reduction. Remember, something can't lose electrons, oxidation can't happen unless there is something there to gain the electrons or accept those electrons. An atom can't lose electrons, kick them out, unless there's something there to take them. All right, so I can't have oxidation without reduction, so these things are called redox reactions. They're a combination of both things happening simultaneously. So I left you with some questions yesterday. I was going to collect 1, 2, 3 here as a little assignment, but I think I'm just going to take them up. I'm going to try not to assign any more assignments from here on in that are unnecessary, and I'm hoping that means we don't have any more between here and the end. All right, so let's look at question 3 there above. That looks at the oxidation, the redox reaction involving iron 3 oxide and aluminum. So let's go to our whiteboard here. And let's start with the mini activity question 3 on page 328. Okay, so question 3 says write the half reactions. So the reaction says Fe2O3 is going to react with 2 aluminums, and I'm going to end up with 2 irons and an Al2O3. Again, notice it's Al2O3 because the oxygen is a -2, aluminum is a +3, so the 3 comes down and the 2 comes down. Same thing over here, iron 3 oxide, the iron is +3, the iron is oxygen is -2, so the 2 comes down and the 3 comes down. Okay, again, just what we've always done. Okay, so notice here's my single displacement reaction going on. The aluminum's going to kick the iron off, and the iron is going to come free. So I'll end up with iron and aluminum oxide because, like I said, the aluminum is going to replace the iron there. So a couple things are happening. My iron 3 plus is on the left, and I've got iron on the right. Notice that I've got 2 irons on the left, but I also had Fe2. I also had 2 irons on the right. Now I also have aluminum here, so I've got aluminum, of which there are 2, is going to get converted into Al2O3, so I'm going to get 2 aluminums, but again, remember, the 3 down here represented the aluminum's charge. We've crisscrossed, like we started in grade 10. So aluminum is +3. What about oxygen? Well, oxygen doesn't change. Oxygen was -2 here, and oxygen is still -2 here. It doesn't Leo or grr. It's not gaining or losing any electrons, so we're not worrying about it. I'm only looking at the half reactions for what is gaining electrons, what is losing. So let's look at the iron first. I'm seeing that I have 2 Fe3 pluses on this side, so I've got a total of 6 pluses on this side and nothing on this side. So I have to add electrons to one side to make it work. I have to add 6 minuses here to cancel the 6 pluses, and that will mean I'll have nothing on this side and nothing on this side. So I'm going to add 6 electrons to the left side here. Down here I've got no charge on the left. I've got 2 times +3 on the right, so I've got +6 on the right. So I'm going to have to get rid of those 6 pluses by adding 6 electrons. Remember what I said yesterday? I think it's easier to figure out which one is the grr, which one is gaining electrons, is the one that's adding electrons. I can see that the iron is having 6 electrons added. It is the GR, it is the reduction reaction. And the aluminum is becoming aluminum 3+, plus it's freeing up 6 electrons that are going to be lost. Leo. Okay, so the question says, write the half reactions. So we've just done our half reactions. There's 1 and there's 1. And it says which one is being oxidized and which is reduced. The aluminum is oxidized and the iron 3+ is reduced. Okay, so there's 1, 2, 3 marks for the test. Right, a mark for this, a mark for this, and a mark for saying which is GR and which is Leo. All right, so 3 marks on the next test for that question. If I go back to, the textbook for a minute, number 4 says identify which change represents oxidation and which change represents reduction. So if I look at number 4 there, I can see 4A has no charge on the left, 2 pluses on the right, right? So I've got to get rid of the 2 pluses, so I'm going to add 2 electrons to the right, which means the copper is becoming an ion plus 2 electrons. It is giving up its electrons. So there's oxidation. I have 3 plus on the left and 2 plus on the right. How do I make them the same? By adding electrons. If I add an electron to the left, the negative will bring the 3 plus down to 2 plus. So I'm going to add 1 electron on the left side, which means the iron 3 plus here is my GR. It's gaining electrons. Okay, so always look at the charge to figure out which side is gaining or losing electrons. Case number 6 here says identify these, which one is oxidation, which is reduction. I can see again, look for the one that's adding electrons. The second one is. So this is my GR. Iron 3 plus is gaining electrons. It's being reduced. The aluminum here is becoming an ion, plus it's giving up some electrons. That's my Leo. Notice that the aluminum, there's a mistake there. It should be 3 electrons. Right, it should be 3 electrons. Because I'm going from Al to Al3+. There's another mistake there too. Look at that. The iron 3+ is going to iron. So to do that, it has to have 3 minuses added to it, or 3 electrons. So if I add up all the reactions, I'll end up with aluminum plus Fe3+ plus 3 electrons on the left side of the arrows. And on the right side, I've got aluminum 3+ plus 3 electrons plus an iron. But notice that I've got 3 electrons at the beginning and 3 at the end. So I can't really include electrons in my reaction, but I usually write them in, because if one of them was 2 electrons, like if I had, okay, so you can see here that I've got it worked out. Aluminum plus Fe3+ makes aluminum 3+ plus Fe. Okay, so there's my reaction. If I had calcium, if I had aluminum, if I had this one here, and I have calcium becoming calcium 2+ plus 2 electrons. So there's my Leo. Right, there's my oxidation reaction. So if these 2 reactions are happening together, if I add those 2 up, notice what I've got. I have Fe3+ plus 3 electrons plus a calcium makes, Fe3+ plus 3 electrons plus calcium on the left make iron plus calcium plus 2 electrons. And, okay, hang on. I can see there's going to be a problem here, in that I've got more electrons on this side, 3 of them, and only 2 on this side. 3 were needed. But I only made 2. That's impossible. I have to have the same number of electrons on both sides. That tells me that I've got to balance this equation. So I've got to find a way to make it work. If I double the top reaction, if I double this one, oops, slide this over. Then I end up with 2 Fe3 pluses plus 6 electrons makes 2 Fe's. And if I triple this one, I get 3 calcium plus 3 calcium makes 3 calcium, 2 pluses plus 6 electrons. And now my 6 electrons here will cancel with the 6 electrons here. Right? And then I end up with the reaction that I'm looking for. That says 2 Fe3 pluses plus 3 calciums. That was 6 electrons. Gives me 2 Fe's plus 3 calcium 2 pluses plus 6 electrons, and now my 6 electrons can cancel. All right, so again, it's important to be watching the electrons as we're doing these things. So oxidation and reduction half reactions, oxidation and reduction being worked together to make a redox reaction. Okay, I want to continue on into our note. To look at probably the most complicated thing in this section. Actually, I'm going to do one more question from yesterday before I move on. This question here, B, right here, it says 2 sodiums reacts with a bromine liquid to make 2 NABRs. So notice what my 2 half reactions are. I have 2 sodiums on the left and 2 sodium ions on the right. It's a bit bigger. And I have a Br2 on the left and 2 bromide ions on the right. So here's this NABR is an Na ion and a Br minus ion. All right, so I've got 2 Na plus ions and 2 Br minus ions. Okay, so notice what I've got here now. Again, trying to make my charges work out. Boy, this is a mess. Trying to make my charges work out. If I look at the first one, I have no charge on this side, but I have 2 pluses on this side, so I need 2 minuses. So I'm going to add my electrons. If I look at the second reaction, I have 2 negatives on this side and nothing on this side, so I guess I need 2 more minuses on this side. So I can see again which is the GR. It's the one that's gaining electrons, which is this one. So my bottom one here is the reduction reaction, and the top one is my LEO. It's losing electrons. Okay, so you're going to get kind of tired of hearing this, but you'll get used to LEO and GR, what's gaining and what is losing electrons. Now notice that in every reaction here, we've got metal, nonmetal, metal, polyatomic ion, metal, polyatomic ion, metal, polyatomic ion, metal, polyatomic ion, metal, nonmetal. This was copper 2 chloride, metal, nonmetal. This was zinc chloride, metal, nonmetal. Everything until here has involved ionic compounds, right? And that means we've got a metal and a nonmetal. However, in reality, we've got just as many reactions in the world that don't involve ionic compounds. They involve molecular compounds, where I've got a nonmetal and a nonmetal, where neither is gaining electrons or losing electrons. But they're still redox reactions. Well, that's impossible, because a redox reaction means I have GR gaining electrons, and LEO, I have losing electrons. How can we have a redox reaction if nothing gains and nothing loses electrons? Remember from earlier in the course, we talked about the fact in the last unit, we talked about the concept of electronegativity. We said that when atoms are sharing electrons, especially non-metals, when they share electrons, some have a higher attraction for electrons than others. And because of that, they kind of take on a partial negative or a partial positive charge because they're pulling the electrons closer to themselves. They don't own the electrons. They don't become negative or positive. They just kind of have the electrons closer to their end, which means they are they're a little more negative or a little more positive depending on which end of that bond they're at. So when I look at this reaction down here, okay, so let's just go back to my note here. So like I said, everything so far has involved metals, which means they are ionic compounds, right? Which means electrons are truly being Gur and Leo. They're being gained and lost. But if I've got non-metals reacting, because ions aren't formed, right? No ions are formed. The atoms basically are going to change the way they share the electrons. Okay, so because they're pulling electrons more towards themselves, they are acting like they have a charge, even though they really don't have a charge. Okay, so instead of calling it an ionic charge, because it's not an ion, we're going to call it an oxidation number. That represents the quantity of electrons that is pulling towards itself or losing from itself. So when I look at SO2 here, this reaction between sulfur reacting with oxygen to make sulfur dioxide gas, I think, okay, what's being Leo and what's being Gur? Well, we're going to come to these questions now, and we're going to start assigning what we're going to call oxidation numbers. Oxidation numbers represent kind of the artificial charge. It's the charge that the atom kind of feels like it has, even though it hasn't really gained or lost any electrons. So, what I know is for a neutral compound like sulfur dioxide here, right? It's got no charge. It's just a compound. The atoms are sharing their electrons. Now, because of that, I know that all the oxidation numbers in that compound have to add up to 0. So this is going to be a little bit bizarre until we do a few examples, and then you'll realize it's pretty straightforward. Now, I know that in an ionic compound, oxygen, which is a 2- ion, because it's got 6 valence electrons, it wants 2 electrons, so it will steal 2 from wherever it can wherever it can find them, and it will form an oxide 2- ion. And that's what oxygen does. It's doing the same thing here. It's reacting with sulfur, and it's going to say to sulfur, I will share my 2 electrons with you if you'll share 2 back with me. Now what that does is the oxygens now are feeling like they have -2 charge. These 2 oxygens these 2 oxygens right here are each sharing electrons with sulfur, but when sulfur tries to share them back, oxygen says, yeah, I'm going to share, but I'm going to hold them closer to me. So what that means is those 2 oxygens are acting like they're -2s, right? So if they both act like they're -2s, and the total charge of the compound is 0, because SO2 has no charge, that means the sulfur, if I do the math, 2 times -2 here becomes +4, right? Becomes -4, I'm sorry. Yikes. Becomes -4, and then the -4 goes across to the other side to become +4. So the sulfur becomes +4 because the 2 oxygens are both -2, which makes up -4, and they have to add up to 0. Okay, now, don't quit now. We're close. And you're going to see that there are some rules here. You're going to have the rules to help you on our last electrochemistry test, which will probably be at the end of next week. And we're going to do lots of practice between now and then. and you're going to have these rules to help you. So here are the rules. When I look at compounds, if I've got an element that's on its own, okay, the element could be potassium or hydrogen or phosphorus, right? Anytime I have an element that lives on its own. Now, remember, hydrogen never lives as H. It will always be on Earth as an H2. Phosphorus is a compound that we often find in the planet as P4, where 4 atoms of phosphorus kind of coupled together. Right? They're not really bonded together as such, they're kind of coupled together. And ultimately, because if I've got two H's together making an H2, they will share electrons, but neither is stronger than the other, so neither can pull them from the other, and that means the hydrogen, we usually write the numbers underneath, has an oxidation number of 0, and this hydrogen would have an oxidation number of 0 because neither is holding the electrons closer to itself. Okay, so hopefully there's our first rule. So in an element, in an uncombined element, it's an element on its own, carbon, magnesium, sodium, lithium, helium, neon. An element on its own always has oxidation number of 0. Okay, so there's my first rule. Again, just kind of bear with me as we go through these 7 rules, and then we're going to do a whole pile of examples. By the end of tomorrow, you'll all be experts at oxidation numbers, right? This, when you first started looking at the periodic table and you're looking at atomic masses and atomic numbers, you probably went, this is really overwhelming. I mean, I just don't think I can do this chemistry. And by now, you just kind of look at the periodic table and you go, yep, okay, so what do I do with this today? So this is kind of the same. So if I look at an ion, right, the ion could be a calcium ion, it could be a lithium ion, it could be a sulfide ion, it could be a chloride ion, right? It could be any type of ion. The oxidation number for any ion, simple ion, is its ionic charge. So easy. Calcium 2+, its oxidation number is +2. Lithium 1+, its oxidation number is +1. Sulfur 2-, its oxidation number is -2. Chloride 1-, its oxidation number, -1, its 1 is -1. Okay, rule number 3. I'm going to get rid of the exception here because we're not going to do any exceptions. Rule number 3 says hydrogen is always +1. Unless it's on its own as an element, in any compound, hydrogen will always be +1. So here, we're not going to look at this example. Here, hydrogen is +1. If I have HCl, hydrogen's +1. If I have H2O, hydrogen's +1. If I have H2SO4, hydrogen's +1. Okay, so hydrogen in a compound will always be +1. If I see oxygen in a compound, again, we're going to ignore the exceptions. The exceptions are things that say hydrogen won't be +1, but 99.9% of the time, oxygen is +1. Right? It's the same thing as looking at humans and say humans are born with 10 fingers. Think, okay, that's a trait of humans, right? We all have 10 fingers. Well, not really, right? There are probably people who are born who are missing a finger, right? Maybe you even know somebody who's been born missing a finger. But I would say as a good generalization, humans typically have 10 fingers, and there are a few exceptions, but they're rare. The same thing with these exceptions here. They exist, but they're rare, and we're not going to get into them because they're just so rare. The same with oxygen. If I've got oxygen in a compound, it's going to have an oxidation number of -2. In water, right? In water, oxygen's -2. In magnesium oxide, it's -2. In hydrogen nitrate, it's -2. If I move on to the group 1 element, sodium, lithium, potassium, rubidium, cesium, and francium. Those elements always, they're in the group 1 column of the periodic table because they usually form +1 ions. We know that already. And because they form ions, we know, according to Rule 2, that ions always have the oxidation number, which is the same as their ionic charge. So potassium will always be potassium 1+. Magnesium, which is a group 2 element, are usually +2. They're in the second column of our periodic table, and they will have ionic oxidation numbers equal to their ionic charge, which is +2. Okay, rule number 6 says if a compound is neutral, the oxidation numbers must equal to 0. Okay, the sum of the oxidation numbers in a compound must be equal to 0. Right, so it doesn't matter what compound we're looking at. Again, let's just look at, say C2H6. Let's look at ethane from our organic unit, and it doesn't matter what we're talking about. Hydrogen will always be +1, so hydrogen here is +1, and we'll have to calculate the carbon, right? And they'll have to add up to 0. So if I've got 6 pluses from hydrogen, I have to have 6 minuses from the carbon, and there's 2 of them, so the carbons are actually going to work out to be -3. So 2 minus 3s makes -6, and 6 plus 1s makes +6, so they add up to 0. Okay, let's get rid of that. Get that messy stuff out of the way. Okay, and then the last one says if I have a polyatomic ion like hydroxide or nitrate or sulfate or chlorate or carbonate, the sum of the oxidation numbers will actually add up to the charge of the polyatomic ion. So if I have a hydroxide there, I see 1 oxygen and 1 hydrogen. We know that oxygen's always -2, right? That's rule number 4 up there. Oxygen's always -2. I know that hydrogen is always +1, right? Hydrogen is always +1. We're ignoring the exceptions. So -2 plus +1 equals -1. So they will always add up to the ionic charge. Sum of the oxidation numbers for a polyatomic ion will equal the ionic charge. Okay, so what are those 7 rules? How do we use them? So if I look at the question I've got here, I've got zinc reacting with oxygen to make zinc oxide. Zinc is on its own, so it's 0. Oxygen is an element on its own, it is 0. In the compound here, I see zinc oxide. I usually look for hydrogens and oxygens first because they're easiest. So I see oxygen there. I know oxygen, let's make this bigger. Oxygen is always -2, right? That's what rule number 4 was. Oxidation number for oxygen in a compound is always -2. Now notice, this is the compound. This is the compound we're talking about here, zinc oxide. So if the oxygen is -2 and the whole thing has to be 0, the zinc has to be +2. Now, sometimes it's not quite as easy to figure out as that, but I know that the zinc numbers plus the oxidation numbers have to add up to 0, right? Because that was rule number 6 up there. The total of the oxidation numbers must add up to 0. Now, so zinc was unknown. Oxygen we know is always -2. So the -2 goes across to the other side as +2, and zinc equals +2. So I can always calculate my missing number, right? Zinc wasn't in the 7 rules, but I still know it's +2 because oxygen was in the 7 rules. Now, we're not going to look at half reactions there yet. We're just going to look at oxidation numbers. So it says determine the oxidation numbers of nitrogen. I'm going to do all 3 here. So I've got KNO3. 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 So I see two elements there that I know automatically what their oxidation number is. Oxygen's always -2, and potassium is a group 1 element, and we already saw up in the rules that the group 1 elements are always +1. So I know that maybe in your head you can figure this out. I can see that there are 3 oxygens that are -2 each. So that's 6 minuses, but I only have 1 plus, so nitrogen has to be 5 plus. Now, if I couldn't really see that, because sometimes it get a little more tricky than that, I can say the oxidation numbers for potassium plus for nitrogen plus the oxygens all add up to 0, because it's a neutral compound, KNO3. Potassium was +1. Nitrogen I didn't know. Oxygen was -2. So 3 times -2 is -6. So let's take the -6 across to this side as +6. Take the +1 to this side as -1. And nitrogen is left over as 6 minus 1, which is 5. So I can calculate my nitrogen up here. As +5, either just by inspection, by just looking at it, or by doing the little calculation thing here to try and figure it out. Let's look at a couple of more examples, and then I'm going to stop there for today and leave you with some of these to work on your own. Okay, so I've got sodium phosphate, Na3PO4. Na3PO4. Okay, so I see 3 elements, sodium, phosphorus, and oxygen. Oxygen's always -2. Sodium is always +1 because it's a group 1 element. So I've got to figure out what phosphorus is. So I know that the 3 sodiums plus the phosphorus plus the 4 oxygens will all add up to 0. Right, 3 sodiums plus phosphorus plus 4 oxygens will all add up to 0. The sodiums are +1. Phosphorus I haven't figured out yet. Oxygen's always -2. So I'm going to take my 4 minus 2 here, which is -8. 4 times -2 is -8. I'm going to bring that across to the other side as +8. I see 3 plus 1 over here. I'm going to scratch that out, which is 3. I'm going to bring it across as -3. So I'm left with P on the left side, and I'm left with 8 minus 3, which is 5. So my phosphorus here is going to be +5. So the sodium was +1, the phosphorus was +5, and the oxygen was -2 always. Again, you can just double check. Oxygen, 4 -2s is -8. And if I look at the positives, I've got a phosphorus, which is 5, and 3 plus 1s is 3 more. That makes +8, and -8 equals 0. So there's sodium phosphate. Okay, the trickier one is this second one, which is a phosphite ion, PO3, 3 minus. PO3, 3 minus. So how do I do something that has a charge? Well, it's very similar to the one we just did. PO3, 3 minus. I know that oxygen is -2, always. So I know that phosphorus plus 3 oxygens have a total charge of 3 minus, right? Because it's an ionic compound and it has a charge of 3 minus. So oxygen we know is -2, so phosphorus plus 3 times -2 is -6 equals 3 minus, or -3. and I'm going to take my negative 6 across to the other side as plus 6. Plus 6 and minus 3 equals plus 3. So phosphorus here becomes plus 3. Now, if I want to just double check here, there's 3 oxygens and they're all minus 2. So that's minus 6. And I have 3 pluses. So 6 minuses and 3 pluses. I have 3 extra minuses. There we go, 3 minus. Okay, so you can see how those 7 rules work. I'm going to recommend that you keep those 9 rules handy. Oops, undo. Keep those 7 rules handy. Right, I've scribbled all over mine. Keep them handy and use them to do the math. It won't take you long to always remember that hydrogen is always a plus 1, oxygen is a minus 2. They're the first things I look for. And elements are always 0. If there's an element on its own, the element will be 0 if it's on its own. So, let me think of an example here. If I got carbon, let's go to my whiteboard. If I look at HClO3, right? Oxygen is always minus 2, hydrogen is always plus 1, right? So I've got hydrogen plus chlorine plus 3 oxygens make 0. So hydrogen was plus 1 plus my chlorine plus negative 6. 3 oxygens is negative 6 equals 0. Negative 6 becomes plus 6. My plus 1 becomes negative 1. 6 minus 1 is plus 5, so chlorine is plus 5. Now there's also a compound that is HClO2. It's a different type of acid, right? One is called chloric acid, one is called chlorous acid. And HClO2, again, oxygen is minus 2, hydrogen is plus 1. So if I did the math, you can see the 2 negative 2's for the oxygen here make negative 4, and I have a 1 plus, so I guess I need 3 more pluses. So chlorine here is plus 3. Chlorine up here was plus 5. Down here, chlorine is plus 3. So it's not like they're always the same. Hydrogen will always be 1, and oxygen will always be minus 2. Right? If I give you helium, it's 0. It's got no charge because it's an element. If I give you bromine, it's 0 because it's an element. It's on its own. Right? There's actually a form of sulfur which is S8, and again, it's going to be 0. It's on its own. Right? If I give you a chunk of calcium, it's going to be 0 because it's an element on its own. So you'll see these rules for oxidation numbers. They take a little bit of getting used to, but they're not bad. And the rules are in the textbook. The rules are in the note. So just keep them handy as you're working through these questions. So there are 2 questions here that are asking you to do oxidation numbers. And then there are some more questions in our textbook, 7 and 8 on page 330. And I am going to stop there for tonight. So you have a good day.